Hi everybody, welcome to the recap video for week 7 of Stats 220 Online. Last week you were watching modules about the robustness of confidence intervals and confidence intervals for the mean. So let's just review what happened last week. So confidence intervals for the mean, the issue is that sometimes we don't know the population standard deviation. In fact, in a lot of applications we just don't know it. So what we do is we plug in a sample standard deviation. So if the data were normal, then we could take the average value, x bar, subtract the mean, and divide by the standard deviation of the mean, which would be sigma over root n. This would then be normally distributed with mean 0 and standard deviation 1. But in most of the times, we actually don't know sigma. So that's the problem. So what can we do? Well, we can plug in the sample standard deviation, s over root n, for sigma over root n. So we plug this in. Plug this in. But then what happens is the distribution of x bar minus the population mean divided by its standard deviation is no longer normally distributed. It has a t distribution on n minus 1 degrees of freedom. So what are the properties of this t distribution? Well, it's a bell-shaped curve that's symmetric just like the normal, except it has this extra parameter called the degrees of freedom. And in the table for the t distribution, that's outlined over here. So each row corresponds to a different degree of freedom. So how do you read this table? Well, let's go through it. Let's pick a degree of freedom. Let's say degree of freedom 5 over here. Okay, so what are these values along the 1.48, 2.02, 2.57, 3.36, and 4.03? Well, they're the values along the x-axis. So the t distribution on 5 degrees of freedom looks something like that. It has a center of 0, and the values, let's say 1.48, 2.02, 2.57. So what this gives you is if you look up and you see one tail, it's 0.1. So that means that the area to the right of 1.48 is 0.10. And because of the symmetry, it's also symmetric, so the area to the left of minus 1.48 is also 0.10. And similarly, 2.02, the area to the right of 2.02 is 0.05. So here, this area over here is 0.05, and this area here, 2.02, negative 2.02, the area to the left of that is also 0.05, etc. So the values that you see in the table are the values of the x on the x-axis, and where it says one tail, two tail, those give you specific areas, and those x-axis values correspond to the different areas. So that's how you read this table. So what are the assumptions behind the confidence interval for a population mean? Well, there's two assumptions. One is that the observations are independent, and two is that the observations come from a distribution that's nearly normal. So what does that mean? Well, it means that basically the nearly normal condition really means that for very small samples, the data should follow a normal model pretty closely, but it's sometimes really hard to tell for really small data sets. So for moderate samples, let's say n between 15 and 40, these t methods work well as long as the data isn't strongly skewed. And when the sample size is larger than 40 or 50, the t methods work, like the t confidence interval methods work really well as long as the data is not extremely skewed. And we say that the t confidence intervals are robust against the violations of normality. So the real practical interpretation is if the sample size is greater than 50, then that's usually enough, unless the data is extremely skewed. You may need a larger sample size. So in the video, there was a simulation with a sample size of 40 where the actual coverage was 90, but the nominal coverage was 95%. So what you would need here is that basically a larger sample size to boost the actual coverage to its nominal value. So one thing that I just wanted to clear up is, what is this idea of coverage? Well, the confidence interval aims to basically contain the unknown mean or proportion with a given probability, and that's often set to 95%. So the confidence level of 95% is often called the nominal coverage. But the coverage probability, the number of times that it actually covers it, is called the coverage probability. So if all the assumptions are met, then the nominal coverage is actually equal to the actual coverage. If the actual coverage is greater than the nominal coverage, then we say that the confidence interval method is conservative, and if the actual coverage is less than nominal, then we say that it's anti-conservative. Now let's go over here to the hand-in problem for this week. So it says that the values of chlorophyll A for a random sample of 25 lakes in a region are given by this data. The sample mean of chlorophyll A is 50.3 and the standard deviation is 50. What is the parameter of interest? Give a practical interpretation of the parameter. So the parameter of interest here is the mean of chlorophyll A among all the region's lakes. A 95% confidence interval can be found for the mean just by simply plugging into the formula. The challenge here would be if I didn't give you the mean and standard deviation, then it would be calculating it. Otherwise, it's just a straightforward calculation. Part C, are the assumptions for the t-confidence interval violated since the data are right skewed? Here, the solution that I put in is that the nearly normal condition is met since the data are not extremely skewed and there are no extreme outliers. This is what it means when we say that the t-test is robust against non-normality, because you can see that the distribution of the values is right skewed, but because there's not a lot of large outliers, that the t-confidence interval should be robust against normality, which means that it should have the appropriate coverage. The next question is that Arctic researchers have used various methods and data to estimate when the Arctic Ocean summer ice will melt completely. Suppose the 50 different experimental data sets were used to calculate 80% confidence intervals for the proportion of melted ice to date. What can be said about the confidence intervals? The first statement is that approximately 10 confidence intervals will not contain the correct proportion. Well, is that true or not? So, since they're 80% confidence intervals, and there's 50 of them, we would expect that 40 of the confidence intervals will contain the true value, 0.8 times 50, and 0.2 times 50 will not contain the true value of the parameter. So that's true. The second statement, the probability is 80% that each confidence interval contains the true proportion. So this is false. 80% of the 50 confidence intervals will contain the true value of the parameter. It's not that the probability is 80% that each confidence interval will contain the true proportion. And if 90% were used instead of 80% confidence, then all 50 confidence intervals would be wider. This is true. If the confidence is increased, then the width of the confidence interval also increases. How can we find 80%? Well, we can go to the t-table, which we can find here. So if you scroll down to the bottom, the 80% value is Z is equal to 1.28, and for the 90% value, 65. So you can see that in the formula, if you use 1.28 versus 1.65, if you use 1.65, this will lead to a wider confidence interval. The next thing that I wanted to tackle was the group problem number 4 and go through the solution with you. A daily plane leaving London for Paris holds 500 passengers. The number of tickets sold is 525, as the airline expects that some passengers will not show. Suppose that each passenger arrives for the flight independently with probability 0.94. The airline company records the number of flights that are full during 1 week. What is the sampling distribution of the number of flights that are full? Well, to solve this, let's let x be the number of people that show for the flight, then x has a binomial distribution with n equal to 525, because that's the number of independent trials here, and the probability of showing for the flight is given as 0.94. That means that x can be, it's also, x is approximately normally distributed with mean 525 times 0.94 and standard deviation 525 times 0.94 times 1 minus 0.94. And that's the same as a normal distribution with mean 493.5 and standard deviation 5.44. So the plane is full if x is greater than 500. And the probability that the plane is full is just the probability of this event. And you can calculate this probability by standardizing. So x minus 493.5 divided by the standard deviation, which is 5.44, greater than 500 minus 493.5 divided by 5.44, which is equal to the probability that z is greater than or equal to 1.19, which is equal to 0.12. So therefore, the sampling distribution of the number of flights that are full in 1 week is normal with mean 0.12 and standard deviation 0.12 times 1 minus 0.12 divided by 7, because there's 7 days in a week. Thanks for joining me on this recap video, and I'll see you next week online.